Hello grade 10s. Today we have a very interesting lesson in the series on quantitative aspects of chemical change. We will be looking at what is known as the empirical formula of chemical compounds. We will also investigate the percentage composition of compounds. Let's start with a bit of theory before we go to Keke, who will explain all of this in more detail. The empirical formula is the formula that represents the smallest whole number ratio of the atoms in a molecule. An example is C3H8. We also get a molecular formula. This formula is the same as the empirical formula or a multiple of it, and it is based on the actual number of atoms of each type in the compound. For example, if the empirical formula of a compound is C3H8, its molecular formula may be C3H8, or if the ratio is doubled, C6H16, and so on. The other concept that we will investigate is percentage composition. This is the percentage of the mass a certain element has in relation to the total mass of a compound. To calculate the percentage composition, we take the mass of each type of atom in the compound and divide it by the total mass of the compound and then times it by 100. Keke will tell us more about the percentage composition and empirical formula now. Keep a pen, paper and calculator ready for some calculations.
Determining the percentage composition and empirical formula is not just a theoretical question asked in school exams. In industry, chemists and mining engineers calculate these values in their daily work. South Africa is a leader in the field of mining. We have some of the richest mineral deposits in the world and world-class scientists who support the industry. Here at Mintech, for example, scientists analyze rock samples to determine what percentage of different elements the rock samples contain. They use a scanning electron microscope. This special machine can give a reading of the exact percentage of each element present in a particular sample. They can then design the most economical method for extracting metals like gold, manganese, platinum, and iron from their ores. Now, unfortunately, not everyone can afford an electron microscope. So, for the rest of this lesson, we will look at the way in which we can find the percentage composition and the empirical formula of a compound by doing some chemical calculations. Finding the percentage composition and the empirical formula is a useful way of comparing the amount of a particular substance in two different compounds. For example, it can help us to tell which of the oxides of iron, iron 2 oxide, or iron 3 oxide contain the larger proportion of iron. This would be very useful information for someone who needed to extract the maximum amount of iron from iron ore. We will start our lesson by joining Aaron as he reacts iron with oxygen to form one of iron's oxides. We will then use the data that he collects as he does the experiment to calculate the empirical formula and the percentage composition of the compound that forms as the product during this experiment.
Hello there guys, I've used the electronic scale to get the exact mass of the iron filings in the glass tube, and I found the mass to be exactly 0.28 grams, and I've collected the data in a simple table over here, and I've also filled the gas syringe with oxygen gas, and at the other end of the glass tube I have an empty gas syringe. Now what I'm going to do is I'm going to heat the iron filings in here while pushing the oxygen over it from the one syringe into the other. Wow, look at the glow. Well, clearly a chemical reaction has taken place. Look, there's very little oxygen left in the syringe. So the oxygen must have reacted with the hot iron in here to form a compound. And that probably is one of the oxides of iron. But at this stage, we don't know the chemical formula. So we need to do some measurements followed by some calculations. So what I'm going to do first is to find the mass of the product. Can you notice that the mass of the product is greater than the mass of the iron we started with? Can you explain the increase in the mass? Well, The mass of the iron did not change during the reaction. So this must be due to the fact that oxygen reacted with the iron to form an oxide of iron. Now all we need to do now is to find the mass of the oxygen which reacted with the iron to form the oxide. And we can do that by subtracting the mass of the iron from the mass of the product. And that should give us 0.08 grams. Now let's go back to studio and see how we can use this data.
I hope you enjoyed watching that experiment. The data that we got from that experiment is extremely useful. Let me show you how we can use it to find the percentage composition and the empirical formula of the compound that formed. Let's find the empirical formula first and then have a look at the percentage composition. Remember, the empirical formula tells us the simplest whole number ratio of atoms found in the compound. This can then be used to write the chemical formula of the substance. Now, remember, we mentioned earlier that iron has two common oxides, iron 2 oxide with a chemical formula of FeO and iron 3 oxide with a chemical formula of Fe2O3. I wonder what the formula is of the oxide we formed in the lab. Let's find out. We start by calculating the number of moles of iron and the moles of oxygen used in the experiment. Remember, to find the number of moles when given the mass, we can use the equation N equals the mass of the sample M divided by the molar mass capital M. For elements like iron and oxygen, we can look up these values on the periodic table. Why don't you use this equation to work out the number of moles of iron and oxygen used up in the reaction and then fill in the table?
The number of moles of oxygen for this example is 0.08 grams divided by 16, which gives us 0.005 mole of oxygen in the sample. This value can now be filled into Keke's table.
I filled in the number of moles of iron and oxygen on my table. Check that you have the same answers as I have. This tells me that the iron to oxygen ratio is 1:1. So the empirical formula for the product is FeO. Our product is iron 2 oxide. Our next calculation requires us to work out the percentage composition of the iron 2 oxide Aaron made in the lab. Remember, percentage is just a way of showing a ratio by comparing the individual contributions to a total of 100. To calculate a percentage of mass, we take the mass of iron, divide this by the total mass of the product, and then multiply by 100. The answer here is 77.78%. This means that in a 100-gram sample of iron 2 oxide, exactly 77.78 grams would be iron. Can you calculate the percentage of oxygen in this compound? That's right, the percentage of oxygen is 22.22%. Remember right at the beginning of the lesson, I told you that finding the percentage composition and the empirical formula is a useful way of comparing the amount of a particular substance in two different compounds. Well, we can now use the answers of our calculations to compare the two oxides of iron. But before we can compare the two compounds, we first have to find the percentage composition of iron 3 oxide. We can do this by using the chemical formula. The first step is to find the molar mass of the compound. In this case, the molar mass of iron 3 oxide is 160 grams per mole. Next, we have to work out the percentage that each element contributes to the total mass. To find the percentage of iron, we take the relative atomic mass of iron, 56, multiplied by 2, and then divide the molar mass of iron 3 oxide, and finally multiplied by 100 to get a percentage of 70. Because there are only two elements that make up the substance, you could just subtract your answer for iron from 100 to get the percentage of oxygen. But not all compounds have only two elemental components, so it's best that you practice by calculating the percentage of oxygen using exactly the same method. Did you also come up with an answer of 30%? You should note that no matter how many elemental components the compound you are analyzing has, all the answers must finally add up to 100. You can use this as a useful check to see that we have not made a mistake. Now we are ready to compare the percentage compositions of the two iron oxides. Clearly, the iron 2 oxide has a higher percentage of iron than the iron 3 oxide. If I wanted to extract pure iron from rocks, I definitely want to choose the rock with a higher iron content. There is one final type of calculation I want to show you today. Suppose I've been given the percentage composition of a compound either as a result of careful laboratory measurements or as a printout from an electron scanning microscope. Would I be able to calculate the empirical formula of the compound? Have a look at this question. A compound contains 30,4% nitrogen and 69,6% oxygen. What is the empirical formula of this oxide of nitrogen? Let's work through this problem together. Remember that if you say that a compound contains 30,4% of nitrogen, it means that in a 100-gram sample of this compound, there will be 30,4 grams of nitrogen. With this information, we can now work out the number of moles of nitrogen in the compound. Using the formula N equals M divided by capital M, we find that 30,4 grams divided by 14, the relative atomic mass of nitrogen atom, equals 2,17 moles. Now we calculate the number of moles of oxygen. The number of moles of oxygen is equal to 4,35. Now, to find the simplest ratio, I have to divide through by the smallest number of moles, in this case 2,17. So 2,17 moles divided by 2,17 moles gives us an answer of 1. 4,35 moles divided by 2,17 moles gives us an answer of 2. The simplest ratio of nitrogen to oxygen is 1:2. This means the empirical formula for this compound is NO2.
I'm sure you followed the calculations quite easily. We can summarize the steps to calculate the empirical formula. 3 easy steps will bring you to the correct answer. The first step is to determine the number of moles of each element. To do this, we use the formula number of moles is equal to the mass divided by the molar mass of the atom. In step 2, we determine the mole ratio. Remember that the mole ratio is found by dividing each number of moles by the smallest number of moles calculated in step 1. If you have done this correctly, at least one of the answers will be equal to 1. The final step is to multiply the ratio to get a whole number ratio. We don't want any decimals in the ratio. This means we need to multiply all the numbers within the ratio until all of them are whole numbers. This step-by-step process makes these questions quite easy. This brings us to the end of this lesson. Join us in the next lesson where we'll practice more of these calculations. Until next time, goodbye.